Guys, so today we're going to go ahead and continue our topic with chapter 10. So we're looking at 10.8 and we're looking at something called the power theorems. And they have to deal with secants, tangents, and chords and finding their measures. So in the past, we found measures of arcs, measures of angles, stuff like that. But we haven't really discussed how we would find the measures of each of these chords, tangents, or secants, given some information. So that's exactly what our discussion is going to be today and what our topic will be on today. Quick little note, guys. Unfortunately, I kind of messed up my laptop. So it might be a little glitchy, and I apologize for that. I'm going to do my best to hopefully make this work, but it might be slightly glitchy. So just fair warning, guys, that it might be a little off. But hopefully everything goes well. So let's go ahead and get started here. The first thing we're going to talk about, guys, is what happens when we have two chords of a circle that intersect inside of a circle, but not at the center. So let's actually go ahead and draw a diagram that shows that. So here's a circle. We have a center. We have a chord. Let's say I have a chord here and I have a chord here. Okay, so those are my two chords. Now the question is, well, what if I wanted to find the measure of these chords, or what if I had certain pieces of information? Okay, so just to reiterate, this is two chords of a circle that intersect inside the circle but not at the center. Okay, so they intersect right here, which is not the center of the circle. So what is the relationship here, guys? What do we actually know? Well, to figure this out, I'm going to go ahead and label each of these portions of the chord. So this segment piece of the chord and the second segment piece of the first chord. And also I'm going to talk about this first segment of the second chord with this second segment of the second chord. Let's go ahead and talk about all those pieces, and I'm going to actually go ahead and label them with a few letters here. So I'm going to go ahead and call this segment A, this piece of the chord segment B, and then I'm going to actually call this piece of this chord, so that segment, I'm going to call that C, and then I'm going to call this part D. So what is the relationship here, guys? What if I actually wanted to find the measure of any of these portions of each of these chords? Or if maybe the entire chord? Well, the way I would do that, guys, is I would actually go ahead and apply a formula. And here is the formula, guys. It is A times B equals C times D. Okay, this is our formula, guys. So this is our first formula for today. A times B equals C times D. In other words, both portions of the same chord multiplied will equal both portions of the second chord multiplied. Okay, so AB equals CD, or A times B equals C times D. Now that's going to come later on, guys. If we need to prove it, I'll go ahead and show you guys the proof. But for now, let's go ahead and take that as our new formula for today. And again, this is if you ever have this situation: two chords of a circle that intersect inside of the circle, but not at the center. Not at the center. Again, there's totally a way to prove this, guys. For now, I'm going to go ahead and omit that. If we absolutely need to prove it, then we will go ahead and prove it. The next one. A tangent segment and a secant segment are drawn from an external point to a circle. So, here is a circle. Whoops, that's not a circle. Try that one more time. Okay. Here's a circle right here. Let's go ahead and move this thing. Let's try that one more time. There we go, much better. Okay, here's our circle. It says, well, what did it say again? It said I had a tangent segment and a secant segment are drawn from an external point to a circle. So let's go ahead and draw that external point right here. Why not? Okay. Well, it says I have a tangent segment. So here's my tangent segment. Okay. That's a tangent segment. And then it also says I have a secant. Now remember, guys, a secant hits the circle in 2 points. So actually, here is my secant. Okay. All right, that's the full secant that I have right there. My red line is my tangent line. So similar to earlier, guys, what I'm going to go ahead and do is actually label all of the sections or all of the little segments in both the secant and the tangent. So this segment of the the secant, sorry, is going to be A. This little external portion is going to be B. And then finally, this tangent segment is going to be C. All right? Now, just like earlier, guys, just like in the top part, you can actually prove what I'm about to show you right now, okay? But for now, let's go ahead and write down what that formula would be. That formula is going to be C squared equals A plus B times B, okay? And I know that might seem a little confusing for now, guys, but let me show you what just happened, okay? It seems like we took the tangent and we squared it, so I'm going to actually write that right underneath. Tangent, and I squared it, okay? And then what is A plus B? Well, let's see. A plus B, whoops, sorry. A plus B is actually the entire full secant line, okay? So the entire full secant segment. So equals full secant times B, which was just the external portion of that secant segment. So let's go ahead and highlight that here. That's just this piece right here, okay? So let's make sure we understand all three pieces of this equation, guys. So tangent squared, that's this part right here. C squared is basically the tangent squared, equals the full secant, which is A plus B, and times the external portion of the secant, so just part B. So let me go ahead and write that down. External segment of the secant, okay? And that would be B, the outside portion. Again, guys, all of these have their proofs. For now, I'm going to go ahead and omit them, but just know that we can actually prove these, and we're actually going to prove them using similar triangles if we absolutely needed to. But for now, guys, let's go ahead and move on. So again, tangent squared is equal to the full secant times the external segment of the secant. So C squared equals A plus B times B. All right, so that is if you end up with this scenario, a tangent segment and a secant segment drawn from an external point on a circle. All right, so the next one here, let's go ahead and scroll. Sorry guys, like I said, my computer is a little messed up, so I apologize if it takes me a little while to record this today. But let's go ahead and move on to the last scenario. The last scenario says two secant segments are drawn from an external point on the circle. So let's draw, whoops, sorry. Let's go ahead and draw a circle, and we're going to go ahead and draw two secant segments from an external point of the circle. So right here, that's a point outside of the circle. That is one secant. Here's the second secant, okay? So let's just be clear, guys. Let's see what exactly is happening here. So ready? First I had two chords, then I had a tangent and a chord. Oh, sorry, a tangent and a secant, I apologize. And now we have two secants. So let's go ahead and do the same thing. Let's label this information we have here. So ready? This is going to be A. This is going to be B. This portion is going to be C. This portion is going to be D. Okay? And much like what we did up here, guys, much like what we did right here, if you look closely at the secant portion right there, what did I do? I multiplied the full secant times the external piece. So guess what? We're going to actually do the exact same thing here. So the full secant for this first part is A plus B times its external portion, which is just B. So again, let's write that in writing here, guys. You're going to multiply the full secant times just the external segment of the secant, okay? And that's actually going to be equal to, well, very similarly, because the second one is also a secant, guys. This is also a full secant times the external portion of the secant. So the full secant will be C plus D times the external portion of that secant, which was just part D. Okay? That is just part D. So let's finish this off, guys. In writing, what am I actually doing here? I'm doing full secant times the external segment of the first secant, and then also, once again, full secant times the external segment portion of the second secant. Okay, that's exactly what's happening here, guys. So one more time. Let's make sure we're clear. The full secant times its external portion, the full secant times its external portion. Okay, guys? So let me go ahead and zoom out real quick. Let me show you guys what this looks like. And these are our three scenarios, guys. All right? The three scenarios, let's cover them one more time before we actually start doing a few practice problems here. So if you have two chords that intersect somewhere inside of the circle but not at the center, guys, we have a formula to calculate that. And that is each two portions of that chord, so both segments multiplied by one another. So in this case, A times B equals C times D. For the second portion, so for the second scenario, is if I have a tangent and a secant, so we would do the tangent squared, in this case C squared, equals the full secant, which is A plus B, and then times the external piece, which would just be B. And following that same exact logic, guys, for the second part, since we have two secants, we would do the full secant right here. Let me show you. Full secant times the external portion. So full secant times the external portion. And one more time, full secant times external portion. Full secant times external portion. Okay? So for now, let's go ahead and move on, guys. Those are going to be important formulas for this section, guys, and that's actually pretty much going to draw chapter 10 to a close. But let's go ahead and talk about how we're getting these things. So what are the products in the relationships? Where did they come from? Where did the products come from, guys? And here's the catch. I don't know if you guys caught this earlier, but actually I said that we can actually prove these by similar triangles. Now think about that, guys. What do we know about similar triangles? Okay, and this is a key word right here, guys. Okay, so here's what it is. Where do these products come from? Where do these relationships come from? They come from the fact that if I can prove that there's similar triangles there, we know that corresponding sides of similar triangles are proportional. So watch what actually happens here, guys. I can say something like A over C equals B over D, just like that. Okay? Well, remember, this is a key word here, guys. Product, product, product. When did we talk about product when we were dealing with proportions? Well, if I cross multiply these guys, isn't that called the means extremes product theorem? Okay? That's where these come from, guys. We would just basically use similar triangles over and over again, and we can prove every single one of these theorems. Now, maybe for a later video, guys, if I have a little bit more time, I will go ahead and prove that to you. But for now, let's keep going. It says when you are working with chords, what actually gets multiplied, guys? Well, when you're working with chords, like if I have chord number 1, well, you would multiply the first segment of that chord times the second segment of that chord. And if I do that multiplication, it should equal the same as what I get for the second chord. Okay, same thing. The first segment of the second chord times the second segment of the second chord. If I do that, guys, you're just multiplying segment times segment. Or if I come back up here, look closely, A times B should equal C times D. Okay, so always, always, always handle it in that scenario when you're dealing with a chord. Okay, next one. When you are working with secants, what gets multiplied? Well, when I was working with secants up here not too long ago, what did I actually multiply? Well, I multiplied the whole secant times the external portion. So let's do that. Let's talk about that. When we're dealing with secants, we multiply the full secant times the external segment or the external portion of the secant. The external segment of the secant. That's what we do when we're dealing with secants. Now the last one is, well, what do we do when we're dealing with tangents? Okay, and the only scenario that we had tangents for was actually this one right here, the second scenario. What did I do with that tangent, guys? We'll take a look. I basically just squared it. So your tangent, whenever you're dealing with tangents, guys, all you got to do is square them. So tangent squared. Or if you really want to write it like this, you can totally do this. Tangent times tangent. Either way is fine, guys. Just understand how this works, okay? So those are going to be formulas, guys, and I know right now they seem very abstract, like where do they come from? Why do we use these? Guys, the reason we use them is to find the measures of each of these particular segments or each of these particular tangents or secants or chords. But as to where we get them from, guys, again, for a later video, I will go ahead and save that because the proofs are a little bit longer and they're a little bit more involved. So for now, guys, I just want to get you guys acquainted with the process of actually doing these. So let's go ahead and zoom in here. Let's try a few problems, and then I'm going to have you guys try some on your own. So let's go ahead and take a look at, actually, you know what I'm going to do? I'm going to do the left side, and I'm going to give you guys time to work on the right side on your own, and then we'll cover all the answers after that, okay? So here's what we're doing. So this is, what am I, well, the first thing you should look at this, guys, is ask yourself, what's happening? Is this two chords? Is this a secant and a tangent? Or is this two tangents? Well, as you can see here, these are two chords. Well, we have a formula when we're dealing with two chords, guys. A times B equals C times D. We have that formula. Remember, A and B belong to the first chord. C and D belong to the second chord. So, A times B equals C times D. So let's write that down. A times B equals C times D. Okay? Just like that. And we can actually solve for this. So this is going to be 3x equals 18. Oh, so, well, not 18. Equals 12. Sorry about that. 12. And then we're going to go ahead and divide by 3 to get x equals 4. And it's as simple as that, guys. So I just found the missing segment here. The missing segment here would have to be a 4. Okay, and again, guys, the reason where this actually comes from, believe it or not, is similar triangles. When I get a chance to actually prove that to you guys, you're going to see exactly why we use those particular equations. But let's move on to the second one. So what is happening here? Well, in this scenario, in number 3, I see a secant and a tangent. So this is the second scenario, secant, tangent. That's the scenario that I see here. Well, did we have a formula for that? Yes, we did. We had a formula for that. That was the secant squared, remember my secant in this case is the 6, is equal to the full, oh sorry, the tangent, my fault. Let me say that one more time. This is the tangent gets squared, so c squared, okay? Now, we also have a full secant right here. That full secant is x plus 5 times the external portion of that secant, guys, which is this part right here. Oops, that looks bad. But yes, that part there in black, which actually was an x. So times x. But we don't have a c here. Let me go ahead and put a 6 there. Okay, so let's do that. This is going to be 6 squared is 36 equals, well, I could distribute this x in here. And guys, you could write it like this too. Just FYI, I know a lot of you guys are going to want to do it like this anyways. You could put the x first, and then the x plus 5. I actually like that. I prefer that actually too. But sometimes it comes out the other way. But it doesn't matter, guys. Okay? It doesn't matter which way you multiply it. So if we do it like this, guys, I'm going to go ahead and distribute the x. So this is going to be x squared plus 5x. Now, what am I noticing here? Well, what I'm noticing, guys, is that I just have a quadratic term here. Look closely, this is an x squared. That gives me the hint that I'm probably going to have to do some sort of factoring or quadratic formula. But we can't do that until we get this side to equal 0. So how are we going to do that? I'm going to subtract 36 on both sides. So that's going to give me 0 equals x squared plus 5x minus 36. And look at that. That's a trinomial, a quadratic trinomial. And I can actually go ahead and factor that. I don't even have to use quadratic formula, guys. All you're looking for are two numbers that multiply to be negative 36. So are there two numbers that multiply to be negative 36, but that add to be a positive 5? Well, let's see. Negative 1 and 36, negative 2 and 18, negative 3 and 12, negative 4 and 9. Let's see, negative 6 and 6, and I think that's pretty much it. Negative 1 plus 36 is 35, not even close. I want 5. Negative 2 plus 18, that's 16, no good. Negative 3 plus 12 is 9, no good. Negative 4 plus 9 is actually 5. It's exactly what I wanted, okay? So my two factors are going to be x minus 4 and x plus 9. And all I got to do now is set each of these equal to 0. So x minus 4 equals 0, or x plus 9 equals 0. I'm going to go ahead and solve them. So add 4, you get x equals 4. And over here, subtract 9, I get x equals negative 9. Now, I have two answers, so maybe there's two solutions here. Well, let me zoom out for just a second. So think about it, guys. Let's see what happens here. Let me do some erasing so you can see it a little clearer. The question is, can we find the value for x? Well, I just found two values for x. One of them was 4. The other one was negative 9. But think closely, guys. Which one of these actually does not make sense? And hopefully you're saying negative 9 doesn't make sense. Why? Because, guys, how are you going to tell me that this segment measures negative 9 centimeters, let's say? That does not make any sense. So there's only one true answer here. And I know some of you guys like to use set notation. So my only true answer would actually be 4. X equals 4 is the only one that actually works. Okay? All right, last scenario. Let's go ahead and take a look at number 5. Let me zoom in real quick. Okay, so what's happening in number 5? In number 5, I'm noticing that there are two secants. Here's secant number 1, here's secant number 2. So there are two secants. So this is a secant scenario. Okay, well, we have a formula for that, guys. We have the full secant, let's write that down, x plus 3 times just the external portion of that secant, which was 3. Now that must equal the full second secant, 2 plus 4, times just the external portion of that secant, which was 4. Okay, guys? Secant is always the full secant times the external segment of that secant. Okay, always. So, we got a little bit of work to do, but that's fine. No biggie. We can go ahead and do that. Let's go ahead and give that a shot. So first off here, guys, I can go ahead and distribute this 3. Okay, that's going to give me, let's see, 3x plus 9. Here you have some options, guys. You can actually add this first, so that's going to give you 6 times 4. Well, 6 times 4 is just 24. And then you get 3x plus 9. And we just solved like a regular algebra problem, guys. Subtract the 9. We're going to get 3x equals 15. And x equals 5. And actually, that is it. That is my final answer. X equals 5. And again, some of you guys like to write in set notation. That is totally acceptable here. But for now, guys, the answer here is 5. So let me zoom out for a second so I can prove to you that the next 3 problems on the right-hand side, guys, are exactly the same. Check out number 1 and number 2. Look at that. Another set of chords. So you can do that just like problem number 1. Here we have secant here and secant here. So actually number 4 is kind of like problem number 5. And then finally, for number 6, this is a tangent and a secant. Well, we just did a tangent and a secant problem here on problem number 3. So I want to go ahead and let you guys give those a shot. I'll come back so you can double check your answers for those. But for now, guys, go ahead and pause the video at this time and go ahead and try problems 2, 4, and 6 for me, please. Alright guys, so hopefully you had a chance to go ahead and try these out. Now number 2, as I mentioned before you guys try them on your own, I mentioned this was a chord scenario. So we have 2 chords here, and again you're multiplying the segments of each of the chords. So again in this first chord right here, there's 2 segments, there's x and 10. So that's what I multiply, right? A times b would be x times 10, x times 10. Now there's a second chord, this chord right there, that's 6 and 5. So 6 times 5, C times D. Exactly what I showed you guys here, guys. So remember those formulas. They're going to be super handy. Okay, so I multiplied that, guys. No biggie here. So x times 10 is 10x. 10x are equals 6 times 5, which is 30. And then if I divide both sides by 10, we get that x equals 3. So final answer here, guys, is 3. All right. This next one is a little bit more involved here, but in this scenario, guys, we have 2 secants. Here's secant number 1, and here's secant number 2. Now, just in case anyone's wondering, Mr. Dorado, how did you know this was a secant? How did I know both of them were secants? Well, guys, look. Each of these long segments hits the circle twice, guys. That's how I know. So I'm starting from an external point, and if I draw the segments towards the circles, I intersect the circle twice in both of these long segments. That's how I know, guys. So just keep that in mind as you're working through these. So what was the formula for secant, secant actually? Well, as we explained earlier, guys, it's the full secant times the external portion of that secant. Okay, and then you're going to repeat the same process for the second secant, guys. So full secant times the external piece of that secant. So it's just repetitive, guys. At first, I think it's hard to remember the formulas, but really it just becomes repetitive after that point. But pay attention to my color coding here, guys. Hopefully that helped you guys make some sense of this. So the full secant for the first top secant was 1 plus 5. That's the whole thing together, times just the external portion, which in this case was just 5. For the second secant, it was x plus 2 for the full, times the external portion, which was just 2. And if I distribute that out, guys, here's what I get. I ended up with 6 times 5 equals 2x plus 4. After I did that, I combined, I multiplied the 6 times 5, which gave me 30. Then I subtracted over the 4 to get 26 equals 2x, divided both sides by 2 for a final answer of x equals 13. Okay? And finally, guys, last one for today is a tangent secant scenario, guys. Again, here's the tangent. How do I know it's a tangent? Well, it only touched the circle once, guys, right here. That's how I know it's a tangent. How did I know the second one was a secant? This one touches twice, here and here. So that is how you're going to spot those little things, guys. So just keep that in mind. So what was the formula for tangent and secant? It was the tangent squared, so c squared, equals the full secant times the external portion. Okay, tangent squared equals full secant times the external portion of that secant. Using the same colors here from here as I did here, pay attention to how I set up my equation, guys. This was x squared equals 15 plus 5 times 5. After solving that, I get x squared equals 100. And guys, at this point, I actually took the square root of both sides. Now, I'm going to warn you real quick. Technically, the answer here is x equals plus or minus 10. But much like in problem number 3, it doesn't make much sense, guys, to put a negative 10 here. Okay, let me scroll up so you guys can see it. How am I going to put a negative 10? Oh my god, sorry about that, guys. Like I said, my computer's going to be kind of glitchy. How is this going to be negative 10, guys? That doesn't make any sense. How can I say that segment measures negative 10 inches or centimeters or meters? Does not make sense. So actually, even though there was 2 potential answers, a plus or a minus 10, the only actual answer here is a positive 10. Okay? So not plus or minus 10, guys. In this scenario, the answer was actually just 10. Okay, guys, I think I'm gonna go ahead and end the video at this point, but as always, guys, if you have more questions, I would recommend you look back at the notes, look back at this video, pause it as much as you need to, and rewatch as much as you need to. But also, as always, I'm gonna try to make myself available to you guys, so whether that be through email, through a Google Meet, or if you guys want to keep adding more questions that you want me to go over, on that working Google Doc, please let me know, guys. But for now, let's go ahead and end the video here, and then we will go ahead and continue tomorrow. All right, guys, have a great day.